Yes, so we have done properties of adels. The main property you have to remember is this proposition 2.3, that adels mod this adel sheaf ed plus k, this is a finite dimensional object, and this is exactly what we want to study, the degree of speciality of this divisor D. Right, so L minus D, how bad is it compared to the genus? So it can be bigger, basically delta D can be positive, and then when it is positive it gives you these new objects, which is adels mod AD, that we showed. And so once these objects arise, we have to give it a name, so we call them differentials. Okay, so in particular we don't call A mod AD plus K differentials, but we call the linear maps on this to be differential. A mod AD plus K we can continue calling adels, but the linear maps from basically the vector space dual of this. This is a vector space, so the dual of this we call that. That's again a finite dimensional object, we call this differential space. So if you think of adels or functions as non-linear analog of tangents, then differential should be thought of as the engineering differentials, right? When you differentiate a polynomial, what happens? So dx dy. So this differential is a non-linear version of your engineering operators. So these are genuinely new objects. We call this now omega d, big omega d. This is the space of linear space of differentials. And what we have shown is a major result, that over the function field, this is actually just one element. Okay, there is a single element, which is the canonical differential. All other differentials are just multiples of that. Again, the analog of this is, in engineering you have dx or dy as the canonical differential, everything else is a multiple by functions. So this is there are two vector spaces here, right? One is over the base field of constant small k. There it is a infinite dimensional, it's not infinite dimensional, sorry, its dimension is delta d. So over the constants, its dimension is what we wanted to study, delta d. No, wait a minute. That's omega d. Yeah, omega d is finite dimensional. This omega is union of all omega d's. This I don't know. Probably this is infinite dimensional. So over constants it's infinite dimensional vector space, but over function field it's dimension 1. So those are the nuances here. We have covered all this. So all this was towards the proof of Riemann-Roch, right? So let's now continue and finish it in this class. So we'll pick this canonical differential omega, and we consider its associated divisors. So that requires a proposition. So in fact, for any omega in the differential space, the set M omega, we define it to be all the associated divisors, which means that omega is in omega d. Okay, so for a differential there may be many associated divisors, infinitely many. That set is M omega. And this has the property is that this has a unique maximal. denoted by bracket omega notation. Okay, we are overloading the notation here. So bracket omega was also for when omega is a function, we were calling it the principal divisor. Now omega is not a function, it's a differential. So for differential, bracket omega would mean the divisor which is associated to omega and is maximal. Now the only problem is that this maybe, I mean, since there are infinitely many associated divisors, how do you say that there is a maximum one? So what we will show that is that the upper bound is a degree. I mean, there is a degree upper bound. So we can define maximal. Second property is that for all rational functions and for all differentials, the following holds. So if you look at x omega, this is another differential. The maximal associated divisor of this, which is defined above, has to be related by with omega, right? So what do you think is the relationship? The maximal divisor for differential x omega and the one for omega, the relationship is this. Okay, so now we are mixing the two things. So bracket omega is maximal divisor for the differential omega. Bracket x is the principal divisor of the rational function x. Okay, and the three things are related like this.
And where is x omega?
X omega, no. So yeah, big omega is a function, in fact, vector space of dimension 1 over the function field. So x omega is also an element there. It's again a differential, just like x times dx is again a differential. I mean, in engineering. Similarly, here also multiplication by functions is a differential. In fact, how did we define it? Do you remember the definition? Because now we'll need it. So x times omega is defined to be, on an ADEL, its action is first multiply the ADEL with x and then apply the map omega Rx. This is what we will now use to prove the proposition. Okay, so yeah, so for first property I need to show that the divisors associated to a differential are bounded in degree.
What does maximal element mean?
Yeah, so it's not clear what it means and whether it exists. So the proposition will define all this in the proof. First we will show is that the set M omega degree is bounded. Once I have shown that the degree is bounded, then in that bounded degree I can pick anything I want. That's a maximal element.
You mean maximal degree?
Oh yeah, actually I can define maximal also properly here. This maximal is with respect to divisor greater than equal to. That also works. That is correct. So in this ordering which we defined in divisors, in that ordering there is a unique maximal element. But that this chain could have been infinite, so I have to first bound the degree. So let's do that first. So that is through this map. That you have seen last time. So consider the map I, which is from LD to omega 0, that sends a function x. So x plus d is greater than or equal to 0, right? That is the function x. And what we did was we multiplied this with the differential omega. And of course, hypothesis is that omega is in big omega d, small omega is in big omega d, right? Which is just saying that small omega vanishes on AD plus k. Right? So if small omega vanishes on AD plus k, what does x omega vanish on? It vanishes on omega 0. Just check that. This diagram was there last time in a different, in more generality actually. These arrows were there, right? So what I am doing now is taking e to be 0. So LD maps to omega e, it's an injection. These are both small k vector spaces, and this is an injection that we had used last time also. Which means what? That the last time also we used that dimension of left hand LHS is less than equal to dimension on RHS. So which will mean that LD is less than equal to delta 0, right? Because omega d is dimension delta d over the field of constant small k. So let's continue this. So this means that LD is less than equal to delta 0, which is equal to L0 minus D0 plus G minus 1. That's the definition of delta, which is just G. We are interested in degree of the divisor, right? So let's do this again for big D. So again, by the definition of delta D, you have this in which you plug in LD and you get degree. So wait, this is at least G minus 1. So which means that degree is at most LD minus G plus 1. Wait, something is wrong. Which means that degree is less than or equal to G minus 1. And LD I have upper bounded, so I get 2G minus 1. I just needed less than infinity. So degree of all these, this is true for all divisors associated to the differential omega. The degree is finite, right? So with respect to the ordering, you will have a maximal element that's defined. So that completes one part of property 1, that there is a maximal element that's defined, d, let's call it d omega, t sub omega. Why is it unique? We could have taken two different paths, two different chains. So second could be d prime omega, So now what should we do? We should try to get a bigger element than these two. So for that you take the LCM. So take the LCM, which means differentials here. Okay, so if d omega and d prime omega are different, then there will be some curve point at which the order of one is bigger. So LCM will strictly grow, right? We want to contradict that. How do you contradict? You basically show this property. You show that this omega of LCM is equal to intersection of omegas. Why is that true? Basically, you have to take a differential LHS, show that it is in RHS, and so on. Just have to use the definition of omega d being maps that annihilate AD plus K.
So won't the LCM have strictly larger degree than each of those things? So eventually you will exceed 2G minus 1. So that can't be true.
Yeah, so once you have, so this is an identity which is unconditional. Nothing is assumed. I mean, there is no special case here. Once you prove this property, let me just make a remark, leave it as an exercise. Use the fact that AD plus AD prime, I mean, even this identity is true over LCM. So you can show that Adels, I mean, essentially a differential that annihilates D and D prime, it will annihilate AD plus AD prime, and so it will also annihilate A of LCM of DD prime. So which means that it is also a differential for LCM of DD prime. Just show this sequence of simple identities. They follow by almost by definition. So once you have this, now you can continue the proof. So now what this means is, since omega is small omega is both in big omega d and big omega d prime.
I'm confused. Like first you prove that d of d is less than 2g minus 1.
Okay.
Can't you show that for any d this is less than? Wouldn't that imply that for any d this is less than 2g minus, not this m omega? Any d,
Oh, any d.
because for every d we can find an omega. I think
No, omega is fixed here, right?
but that
In the whole proof proposition, omega is fixed.
yeah, I'm saying just take any divisor
Yeah.
and I can find some omega such that it will belong in omega d. Then
No. But why are you changing omega? I don't
that
understand.
would
Small
imply
omega.
that d of the degree of every point is less than 2g minus 1.
No. Small omega I have given you. I have given you a differential.
Yeah, understand. If you have a differential, then you can show that.
Now tell me why. How will you show that m omega is bounded? Degree is bounded.
No, you have shown that for any omega.
No. Why do you keep saying any omega?
The proposition given for any omega in this,
Yeah.
like if d belongs to this m omega, then degree of d is less than 2g minus 1.
So for any divisor d, does there exist omega such that d belongs in M of omega?
Oh, you are saying that there is some problem in the proof.
And that is within, that will show that every point will have a bounded degree, 2g minus 1.
You are saying that this means that every element in the class group, or in fact even in the divisor group, has degree. No, this. Yeah, that's an interesting thing. So you have already jumped to the proof of Riemann-Roch. So what is happening is that if you take very high degree divisors, these objects they just evaporate.
But at a high degree divisor, we can't put them in M omega.
No, because you will see very soon in this class that for high degree divisors, the domain where we are working in, it doesn't exist. I mean, this omega d will be zero dimensional, because it's, see, I guess you already have the intuition. So in the beginning of the class I reminded you that big omega d has dimension delta d. Delta d is the difference of LD minus, I mean the difference basically in the Riemann theorem from genus. For high divisors, that difference will not be there. So all these things that we are doing, they will evaporate. So that is what we have realized. And that is true. That's a fundamental thing we will see very soon in quantitative terms. It's not a contradiction, although it seems to be. Okay. So yeah, so now intersection means that omega is in both, so omega is in LCM. And yeah, as was pointed out in the beginning that well, LCM strictly grows, but since it also contains omega, small omega, so it cannot grow, which means that both the divisors are equal. So this means by maximality that only way out is d omega equal to d prime omega, and that is the uniqueness. And we will denote it by this notation. This will be the notation, same as principal divisor, but now for differentials.
This omega cannot be zero, right?
Sorry?
This omega is not zero, right? Ever? Because
This
then this injection will not occur.
this omega, we can just put that in the hypothesis.
Then the high degree case will be handled.
Correct.
D belongs to
That is correct. Yeah. Yeah. So these objects that we are building and working with, they actually are all trivial in the limit. So this degree of speciality is really a very small, tiny case in the scheme of things. But that is what Riemann-Roch intends to study, right? It intends to study these places where Riemann theorem is non-exact. But generally it is exact. You will see that. Okay, second property that we have to show is this x omega. Now we have defined this bracket of differential. So I want to now understand bracket of x omega differential in terms of omega. So what is that? So we start with this omega, small omega is contained in big omega bracket omega, small omega.
Only when you go and write uniqueness, it's not clear.
Yeah.
How do you uniqueness there? The LCM.
Yeah, that is just in one line. So the by maximality, what you learn is suppose d omega and d prime omega at some point the orders are different. So which means in the LCM the order has actually grown up, has increased. So once it increases, it will basically the LCM will be strictly bigger than both the chains, the d omega chain and the d prime omega chain, which will contradict the maximality of d omega. So it is just contradicting maximality of d omega if it's not equal. Fine? Okay. So now this with this new notation, little omega is in big omega of this unique divisor. And where is x omega? So x omega is in this divisor minus the principal divisor. That's almost by the definition of x omega, because first you multiply the adel with x and then you apply the differential omega. So you have a loss here, that's minus x. So from here I want to claim that the maximal associated divisor for x omega is this. It can't be anything more. So this is simply by the fact that the degree of principal divisor x is 0. So whatever chain of divisors you will follow, so max degree in M of x omega will be equal to the same as degree of omega. You have to show this, and this is a divisor whose degree is also the same. So this is maximal, this is unique. I feel there is one more step here, but you do it as an exercise. This part you can just complete. Yeah, so that's the identity. Maximal divisor for x omega differential is that the previous one minus the principal divisor. Yeah, so what is the advantage of this? So now actually you know that this maximal divisor of a differential I mean, if you consider, if you go modulo principal divisors, it is not changing. So let's write that down, or maybe first state it as a property. So here are your differentials. This bracket notation is giving you a divisor which can be mapped to the class group. So little omega is mapped to bracket omega is mapped to bracket omega modulo the principal divisors. That's the sequence of maps. These are all vector space. These are all at least abelian groups. So there you have these morphisms, and so basically if you multiply on the left, scale up omega by a function x, the image doesn't change. That's all I wanted to say, and from this you can get a definition. So the image of omega above for generator omega, I mean big omega we have shown is a dimension 1 vector space over the function field. So for the generator the image is unique. Although you can pick many generators, but they will all be just multiplying by functions. That will not affect the image. So the image above is called the canonical class of the function field of the curve. Okay, so for all transcendence degree 1 function fields, we have this new object. It's a new invariant, we call it the canonical class. It is just a divisor. It's unique. And
easy is it to calculate this?
yeah, I don't have an algorithm.
You know the degree is 2g minus 2, so there's already a brute force. You have found the multiplication.
No, but you want a fast algorithm. Fast algorithm I don't know, because right now big omega is just this Adel mod Adels, mod sub Adels, and that calculation is infinite. So I mean, sure, you can try brute force, but I don't know how you will verify and all that. Yeah, I can't do it immediately. But at least we can now finish Riemann-Roch. Let's state it again. So let D be arbitrary divisor that we wanted to study, and W be this new thing we have defined, divisor in the canonical class. So then what we will show is actually structurally we will prove an amazing result that this differentials, they are in some sense isomorphic to the L sheaf. Okay, in particular it is the W minus D. That is what kind of the vague intuition we started with. We wanted to understand delta D by some dual of the divisor D, kind of L minus D. So it's LW minus D, and which means that delta D, which is LD minus DD, what was that, plus G minus 1, this is equal to L of W minus D. Okay, so the places where Riemann theorem is inexact, it actually gives you new objects. It seems so that they are new objects, these differentials, but now you see that they are actually old objects because it's just the L sheaf for some other divisor. Right, so this ties all the threads. and its proof now is actually obvious after so much of development. So you just we'll just give you the map, right? So consider phi which sends a function to, as before, x omega. Omega is in yeah, actually I want to say omega is coming from the so W is the divisor, the canonical class is yeah, omega is simply just the generator of big omega. That's all. So you can pick now any generator of big omega, and you know that its bracket, this divisor, maximal divisor associated to omega, is a canonical divisor. I mean, is a divisor which will not change up to multiple by functions. So it's equal to this big W in the class group. So absolutely it may change, but then modulo principal divisors it is not changing. That's all you have to take care. And yeah, so you know already that phi is K linear injection. What we have to show is that phi is a K linear surjection also. Then it will be an isomorphism of vector spaces. So which means that let's take an element differential omega prime and find a preimage. So you know that omega prime and omega will be related by a function up to a multiple, right? So there exists a function such that omega prime is x times omega, which it's right, and I think this also should be remembered, right? Maybe I should not mix these two up. So x is there. Also, you know that that the maximal divisor associated to omega prime, that will be at least d, because d is one of the associated divisors. Omega prime is in big omega d, right? So by definition you also have this, which is a condition now on x omega. And what does this give me? Yeah, maybe I should use a different. So what I need is a y in the preimage. Uh, so I should just take it to be, yeah, so what is this? See, this is just W. So this tells you that W minus X minus D is greater than or equal to 0. Right, so do I have a function in L W minus D? That is X inverse. So this implies that 1 over X is in L W minus D. Does it work? For omega prime, I needed a Y. Oh, but this X is not coming to be.
You just have to show that there is something that maps to omega. in your
To
generation.
omega prime.
Not omega prime, just omega. The rest will follow because everything else is related.
Okay.
If you map to the generator, I think that should be.
No. No, formally you have to do this because differentials are the generator times functions. So whatever you do, this has to follow. But do I already have this or not? I have to find a function which times omega is omega prime.
We have to divide it into cases. If W minus D is less than 0, then no function will exist. Right?
Yeah. Mm-hmm. No, but suppose that is not the case, then I mean, my plan was to use just 1 over x as y, but the problem is 1 over x is mapping to omega over x. No, but that should be okay.
But this is isomorphic to the space L of W minus D plus div x as well.
Mm-hmm.
You can put the x inside the L.
Mm-hmm. So give me a y which will work, which will give me x omega. That I don't see. But can I just change the association? Will it create a problem?
You can do that if it's well defined.
No. Yeah, this is.
If W prime belongs to omega d, then W by x also belongs to capital omega d, and the same argument will tell x belongs to.
No, so
You said you have to differentiate three cases.
y minus y plus y minus d is greater than or equal to 0. I want to check now y omega. What is it on AD? On AD. So there is an R, there is an Adele which is like this. No, I'm worried that maybe it should be omega plus x. I think this minus sign is wrong. I may have to do correction in the previous proof. It should be w plus x minus d. Otherwise, it will not, this will not make sense. So let's just check that. Why should it be omega plus x?
How is this x omega different? Brackets x omega. They are totally different.
Yeah, that has to be corrected, I think. Because other things are fundamental. You can't change anything here. So the only thing which I think I made a mistake is that this should be a plus. X omega should be omega plus x. So w minus x minus d is what you get, which actually gives you x is in LW minus d. So that is the pre-image of omega prime. Which means that phi is surjection. Okay, so it's an injection, it's a surjection, it's an isomorphism.
Is this consistent earlier?
No, it's not consistent. That has to be made plus. This has to be made plus. Yeah, so x, I mean, this has to be checked by definition. So let's call bracket omega d. So if omega is annihilating AD, we are claiming that x omega is annihilating A of d plus x. Should be correct? No, what I have written here. So if omega is annihilating AD, I want to show that x omega annihilates d plus x. So any r here is of the type r plus d plus x, and x omega will multiply this and then it will apply omega on that. Yeah, this part I have to check. Yeah, or if there is a heavy inconsistency, I will correct everything. But let's do this. So with x omega equal to omega plus x, you actually get a pre-image, and then it's an isomorphism, and second thing follows. So delta D is equal to G minus 1. Okay, so basically this proof is hardly anything. We just have to see the development that we have done before this. So from that it follows that the differentials over this divisor D, they are actually this old object L sheaf on W minus D. So that is the statement of Riemann-Roch. There is a sequence of corollaries that are very useful to know. So first corollary is what Rishabh was pointing out before, that if a divisor has high degree, so this becomes quantitative now. If you take a divisor of degree more than 2g minus 1 or more, then Riemann's estimate is exact. Okay, so for bigger divisors, Riemann already is exact. Roch isn't needed in that case. So why is this?
Because L of W minus D will be.
Yeah, so look at the line above, Riemann-Roch statement. So look at L of W minus D. So degree of D is greater than 2g minus 2 is what you are given, and sorry, let's do something simpler first. Understanding the canonical divisor. So L of the canonical divisor is G, and the degree of the canonical divisor is 2g minus 2. So from Riemann-Roch identity, we'll actually get information about this abstract canonical divisor. How do you show this? Yeah, so we can do two things. Since it's true for all divisors, we can try divisor 0 and divisor W. So for D equal to 0, you will get that L of 0, which is 1. So left hand side is G, L of W, right? That's the first property. Second is Riemann-Roch for D equal to W. This will give you L of W, which is G minus degree of W, that is unknown, plus G minus 1 equal to L of 0, which is 1. So which gives you that degree is 2G minus 2. Okay, so for the canonical divisor, you know that the degree is not too big. So as Madhavan was saying, you can try to brute force on this, but still I don't know what the algorithm would be because you don't know the points. You know that somehow 2g minus 2 should suffice, but then there are all these positive and negative orders. You don't know the orders, you don't know the points, so it's not, this itself is not enough. You actually have to go in the structure that we have developed till now and devise an algorithm. Okay, now the next thing, corollary 2. So if the degree of a divisor is greater than the degree of the canonical divisor, which now is 2g minus 2, we know, then Riemann's theorem is exact. The proof of this is simply that since your divisor has a higher degree than W, so W minus D becomes negative degree. Which tells you about its L dimension, that will be. So a negative divisor means that you are looking for functions that is greater than equal to positive. So it should have I mean those functions won't exist except the, I mean in this case not even constant functions will work. So you'll actually get nothing. It's dimension 0 space. Right, because even for constants the principal divisor is greater than equal to 0. So nothing will exist. There is no function. So you can use this now in the formula. That gives you exact. So degree of speciality is 0. So Riemann's expression is LD minus DD equal to 1 minus G. That's true. And third corollary is especially nice. It's used in algorithms. It says that for these high degree divisors, so high degree, so the degree of the divisor is high, but still you may have positive and negative. Both kinds of orders will be present, right? You may have 10 times P1 minus 5 times P2. That kind of thing may be there. So what this corollary says is that you can make all the orders positive in the class group. Okay, so for any high degree divisor with having negative orders also, the negative ones can be replaced by positive if you are only interested modulo principal divisors. Which means that d prime minus d is a rational function where d has negative orders, d prime has only positive orders, and their difference is a function. How do you show this? So for this high degree, you know by corollary 2, So LD is equal to and what is DW? DW was 2G minus 2. So that's 2G minus 2 plus 1 minus G, which is G minus 1. I guess I need G to be positive also. Or not actually. Yeah, G equal to 0 will also be covered, because G equal to 0, you are just saying that the class group is 0. That's fine. And when this when this is greater than or equal to 0, what happens in genus 1? Then it's 0, but it's a strictly greater than, yeah. So this essentially is greater than or equal to 0, which means that LD is positive, which means that a function exists. Right, so there is actually a function. This LD space is not empty, and when that happens, by definition you have D plus X greater than or equal to 0. You choose this as your divisor. Okay, so there is a function that you can explicitly find. So this, by the way, is an algorithm. You are given a high degree divisor, you can compute the LD vector space, and then you can find this function x. In fact, you can take any function x. So you just find one function, you just pick your first function which you find in LD and add it to your divisor, you get D prime. So this is a fast algorithm. So which basically tells you that in the class group, the divisors that you need to study are only sum of points on the curve. Okay, you don't need to worry about the negative order ones. That's a powerful thing, and it wasn't expected when we defined it. A priori, it wasn't clear that this would happen, but this is true in the class group. And also you know that it's efficient because you will never need more than degree many points. So whatever divisor you will take, that many points sum will be equivalent to this divisor. So it's all fast. Yeah, so every divisor has a small positive representation. This sigma pi is the positive representation. Yeah, so the other thing is, or just a small observation, is that we didn't formalize this algorithm to compute genus, right? Because Riemann's theorem was inexact. Yeah, so now actually we can make that algorithm a bit clearer, because what you can do is just start with the high degree divisor, which is 2G minus 1, right? So start with this. So it's a single point, the point at infinity with the order 2g minus 1. Start with this divisor. This is the high degree divisor. Okay, you may ask, we don't know genus, but we showed an upper bound like d square. So there is some upper bound that you know. Let's use the bound B. Yeah, so start with a divisor which is just infinity multiplied by a big enough number, can be degree square for your curve, and compute LD0 minus DD0. That gives you a genus. So LD0 space minus B, which is the degree, is equal to 1 minus genus. Okay, so this is a clear algorithm to compute genus, it's fast. You just have to compute this LD.
But to guess B, you should only.
B we had estimated D square. That comes from Riemann's proof.
B is D square.
Yeah,
What is D?
degree of the curve.
You have a planar curve.
So just from the point at infinity, you can compute the genus by using the LD sheaf. You have a very precise bound when it works.
No, but if you know the degree of the curve, there are even more precise formulas with which you can directly compute it.
Sure. If you work hard, you achieve more. I don't doubt that. Okay, so yeah, the last question is which I have not answered. Be sometime else we can answer this. Give an algorithm to compute W. Okay, so given a transcendence degree 1 function field, how to compute this canonical divisor? That should follow from this theory, but yeah, I'm not sure about the details.
Is this even possible in poly log P where P is an x?
Yeah, so last thing, we don't have much time today. We'll meet again tomorrow. The last thing is this, the motivation, I mean this sigma pi representation, positive divisors, this actually motivates a very important object related to curves, which is this abelian variety, a higher dimensional object which is a new property of the class group. So let's just quickly sketch that. So consider the subset degree 0 divisors like this. Okay, so go over all the subset of G points on the curve and just sum them up, and to make the degree 0 minus genus times the point at infinity. So this is the subset which which we call the Jacobian, but it has amazing properties. For example, you can show that any 2 points, so it is not just a subset, but it's actually an abelian group, which is isomorphic to the class group. Okay, so this is just an explicit representation of CL0. So that's the property that I think we should at least sketch the proof of. We can't do this in detail in this course. We haven't developed the machinery because it's a higher dimensional object. It's not a curve anymore. So we want to show that this is in a way isomorphic to the class group, which also means that any 2 elements in this set you can add and get a third element uniquely. It has the group structure, abelian group structure. I mean, we defined the divisor group so that there is a forced group structure, but so that was not very interesting because it was a free group. So you were getting this in these infinitely many points elements. Here it will be more interesting. Here also it will be infinite, but in fact I should say that it's better to think of k equal to k bar. So points are infinitely many. P1 to Pg are infinitely many possibilities. So of course this also has infinitely many elements, but the representation is nicer. And there are many more things you can actually do that you cannot do in just the divisor group. So first property is this. Why should such a thing happen? So let's just sketch the idea. So for any divisor, I'll call it d gamma. Think of gamma as an index parameter. So for non-negative divisors of degree g minus 1, collect these degree 0 divisors such that the L dimension of d plus 2g minus 1 infinity minus d gamma is 2. So this thing, mysterious divisor, I'll call it d prime. The degree of d prime is 2g minus 1 minus g minus 1 gives you g, and degree of d is 0. So this is degree g. So this is a subset of what? It's a subset of well, I guess, yeah, I don't want to say anything more. Div 0 is the place where it lives. Yeah, so think of a fixed divisor d gamma of non-negative divisor of degree g minus 1. And what is this statement saying? So equal to 2 means that, I mean, there are always these constant functions, but there is a more interesting non-constant function in this L space, right? So you can add it to this d prime and you'll get a positive representation. That is what we want to actually use. So this d has well, there exists a function first of all in L space of D prime such that D prime plus F is greater than or equal to 0, which means that it's a sum of points, right? D prime plus F is a sum of points. So you basically have written this D plus 2G minus 1 infinity minus D gamma, rewritten it as sigma pi. And how many points? So think of k equal to k bar. So degree of all the points is 1. The degree of LHS is g. D prime degree is g. So g many points. Okay, so this is what the subset is doing. It is collecting all these degree 0 divisors plus something which is fixed, right? This 2g minus 1 infinity minus d gamma is a fixed divisor. So don't worry too much about that. So d plus this fixed thing is just a sum of g many points. So what are such d's? You collect them and then you keep changing d gamma. So what you can show is that in the union of these d gammas, you will have all div 0c. That's not very hard to show, but it will need notation we can't develop here. So going over all d gamma, covers div 0. So all the divisors d will be accounted for. So basically you have these patches. As gamma varies, these d gamma are your patches in which you have partitioned div 0. So why did you do that? The thing is that this L d plus fixed thing equal to 2 is a linear, it's a polynomial system that you get in terms of the unknown d. Yeah, so that polynomial system will give you a variety. So D will be a solution set of a variety of an algebraic system. So let's let's write this in a nicer way. So now we can define a nicer looking set C gamma, which is sigma of these points that we got minus G infinity. D is in D gamma and sigma pi is that thing we got from the LD function. Okay, so these are the points that the divisors you get from D gamma, they actually correspond to. So this is a nice object because you can show that this is a quasi-projective variety. Okay, so these divisors, degree 0 divisors which you have, there is actually a algebraic system whose solution it represents. It is still an infinite set because we are in algebraic closed field. In fact, it's always infinite. the way I have defined points. It's always an infinite object, but it's more than just a free sum of points, right? It now actually has become a projective variety. So C gamma is a projective variety, and if you look at the union of all these parts, go over all the gammas, this is everything in CL0. Yeah, that was actually our original definition of JC also. Yeah, so this set JC is now we have found its patches, which are varieties, and you can glue them and you can get a single variety. So this JC set is now a variety which is also a group. So gluing the open patches C gamma, we get or we make JC a variety. And an abelian group. Right, so there are two parts, two facets of JC. So this is the group part, and this is the variety part. Right, so JC has both these facets. It's a projective variety. It's also a group. It's called an abelian variety, and it has dimension quite high, which you can already guess from there. You are summing up G generic points, and each point comes from a curve, right? So it is expected to be dimension G, and that's true. So for higher genus, this object becomes more complicated. It's a higher dimensional variety. And yeah, so for genus 1, what happens? For genus 1, this is just a single point minus infinity. That's the case of elliptic curve. So for genus equal to 1, which is an elliptic curve C, JC actually is curve itself. Okay, so in the case of genus 1, the curve is its own Jacobian, which makes this curve actually an abelian group. That is the reason why elliptic curve forms an abelian group. So it comes from here. So how do you add points here? So P1 minus infinity plus P2 minus infinity, you want to get to P3 minus infinity, right? Which means that you want P1 plus P2 minus P3 and minus infinity to be a rational function. Right, so you, on an elliptic curve, if I give you 2 points P1 and P2, what is this third point P3? So essentially what is done is that you draw a line through P1, P2 and well, the third point you will get its reflection under infinity will give you P3 because of this minus sign. So there is a minus P3 here. So which is why, I mean, are you aware of elliptic curve addition? So you, for P1, P2, you will draw a line. Maybe it can be drawn here. So if so P1 is here, P2 is here. Maybe there is a part here. So when you draw the line, this third point that you get, so the line is essentially the function, and this is the curve. Maybe I should call it L. Yeah, so line is that function which contains P1, P2, so it is uniquely defining L, and this point is then in the formula setting it's minus P3. So which is why there is a reflection that is needed, and that reflection is basically guided by the point at infinity in your embedding. Yeah, so the reflection will give you the P3, and that is the addition which is first of all, it's the Jacobian group addition. Elliptic curve just inherits it. That's the picture.